Welcome to this webinar. My name is Taro Eichler. I'm Technology Manager for Wireless Communication and Photonics, and I have also from the past experience 10 years in quantum optics, so this topic is very close to my heart, and we hope to share this fascination for this topic with you. It's today about 6G and in particular the role of photonics in terahertz communications. And together we will have this webinar with Thomas from Optical Photonics. Thank you very much for joining us today.
Thank you, Taro, for the invitation. And for the demonstration later, I brought a frequency comp and an external conversion to RF to demonstrate the potential of photonics in RF high frequency generation. Back to you, Taro, for the main talk.
Thank you. So let's dive into the topic. Today it's about 6G and terahertz communications. So I will start with a short overview regarding terahertz potential use cases. The spectrum landscape, of course, is a very important part. Then how to generate terahertz radiation via electronic and photonic technologies. We have a project related to this called 6G Atlantic. And then phase noise measurements, in particular in the context of optical frequency comp. Then I will dive quickly into the topic of OAM, orbital angular momentum. Also, we will talk about sub-terahertz communication channels, industrial environments in particular. And then I hand over to Thomas for the demo. So I think you're familiar with this already. 6G research areas have been discussed a lot. Today, we focus on two particular topics. So terahertz I mentioned already in photonics. Besides that, there are many other topics like reconfigurable intelligent surfaces, AI and machine learning, and so on. So we have actually research projects within with German partners covering all these different topics. But today we would like to talk about photonics. So one of the first questions always is, what frequencies do we want to use for the next generation wireless communication? And of course, it's not a new discussion. Already in 5G, the trend has moved towards going to higher frequencies, to millimeter waves. And this trend is continuing, of course, because you need a spectrum. And for 6G, besides the lower frequency region, I'll come back to the topic, frequencies such as D-band, so above 100 gigahertz. The D-band ranges from 110 to 170 gigahertz is, for example, one research area which is discussed a lot, and there's a lot of research ongoing. The 300 gigahertz band as well. So these are the main frequencies above 100 gigahertz, and below that, the W band from 75 to 100 gigahertz or 110 gigahertz is discussed, as well as the area, and this has in particular has gained a lot of interest recently, the so-called FR3 region between 7 gigahertz and 24 gigahertz. But today we will talk about terahertz or sub-terahertz communication. One of the first questions is always, what are the potential use cases? Yeah? And if you go to higher frequencies, then you always have the issue that you have higher path loss, of course, like in millimeter wave already. So there are certain limitations. And here is shown overview from ETSI. Actually, in ETSI there is a ISG, so Industry Specification Group, focusing on terahertz. And they propose some of these use cases related with virtual augmented reality, close proximity communication, and so on. Generally, there are a lot of applications for which the terahertz regime is very interesting. So communication and sensing, that's one area. Here on the left side, you see a chip from the IHP. It's a D-band radar chip. Spectroscopy, well, this is not communication, but still a very interesting area of terahertz applications. So that is, for example, related to maybe fingerprinting or distinguishing between different forms of drugs. So this is, for example, here the drug of Voltaren. And so molecules have a let's say, fingerprint spectrum, especially in this terahertz regime. So for that reason, it's very interesting. And imaging is, of course, also another area. And here on the right side is a picture of done with a QPS, so it's a Rode-Schwarz scanner, but it's strictly speaking between 70 and 80 gigahertz. Yeah? So it's not yet terahertz regime. Then what are the potential use cases for communication? Of course, one area which is rather straightforward and that is already happening before 6G is a backhaul and fronthaul. Point-to-point links. There's even an IEEE standard dedicated to this. Now currently there's E-band, already point-to-point links are existing. That will be extended to the W-band and then to the D-band and so on. So that's a very straightforward evolution. Another area of application are a kiosk, for example, for a kiosk application, so fast download in a restricted area. And you also have device communications. And application in data centers is also something one could imagine. So basically, there are three ways to generate terahertz. It's not so straightforward because, as you know, there has been this terahertz gap. So it's between electronics and between photonics. And so you have basically three ways to generate that coming from electronics, up conversion. So this is kind of the traditional way. We also do a lot with our instruments. Then you have the possibility to do down conversion coming from photonics. That's what I'm going to talk about. And then you have also the possibility to directly generate terahertz radiation via QCL, so quantum cascade laser. So this is a setup from our product portfolio, which is dedicated to testing in the D-band. So from 110 to 170 gigahertz, that's really available, and it will be extended also to other frequencies. And so that is the traditional electronic way, which I will not talk about, but I want just to mention that, let's say, there are already instrumentation available to do testing in that area. But actually today I want to focus on photonics. So I think there can be many applications in photonics. Of course, I don't see it as a substitute for the current electronic technology by no means. Still, electronics is the most advanced and also a miniaturizable and scalable technology, working at room temperature mostly. So, but I think photonics can play a big role on one hand to provide additional tools to electronics where it can help. We will see one example using the optical frequency comp for microwave generation, ultra-high stable microwave generation. We see that in demo later on today. But also there are other ways where photonics can play a complementary role to electronics. And one example is visible light communication that's also mentioned in the context of 6G sometimes. But on the other hand, as well in the core network. So of course, already now the fiber communication is all optical, but there are a lot of electronic optical interfaces. And you want to minimize these as much as possible, which you can do by completely optical switching. So that's one of the activities which actually the IOWN GF, so the Innovative Optical Wireless Networks Global Forum, is promoting to have an end-to-end architecture in the network with end-to-end optical, or let's say photonics communication basically. And the reason is that that's a way to reduce the latency, which is needed for 6G. And also probably a way for very low latency communication as well. So another area which I want to not talk about today, but is an interesting area, and also Rode Schwarz is involved in that area, is quantum communication and quantum networks. So you know that if you transmit single photons, so a photon cannot be copied, it cannot be cloned, and if you measure the state of the photon, which transfers information, then you will change it. And that can be seen at the receiver. So it's in principle not possible to eavesdrop. Of course, quantum key distribution. So for example, exchanging encryption keys via this is one possibility. But in that case, also you need additional classical channel. So that can be still eavesdrops. But anyway, so that's one area which is very interesting and also will be part of 6G, but generally of the network. So we have one research project. So in total, we have Rode Schwarz has 6 research projects by the German Ministry for Education and Research. It's funded, And one of these research projects is so-called 6G Atlantic. The topic is photonic generation of terahertz signals in application for test and measurement. So Toplica is one of the partners in this project. Actually, we are the coordinator. Then Microwave Photonics, Fraunhofer Heinrich-Hertz-Institut, TU Berlin, and Spinner are also part of this consortium. And well, besides generating and analyzing terahertz radiation, one of the topics is also to create very highly stable microwave oscillators, potentially miniaturizes, and also apply this to instrumentation. So I think I mentioned this already, but one way to generate terahertz radiation is down conversion coming from the optical regime. That's what is displayed here. You start with two lasers. They could be, for example, derived from a frequency comp at two frequencies, nu1 and nu2. One of these arms can be modulated by a Macht-Sehender modulator, for example. And then you couple them in a fiber. You have the beat signal. You mix them on a photodiode. So, for example, UTC photodiode, and then terahertz radiation is emitted at the beat signal. So this is in principle not new, but that's one possibility which has not been, still I think offers a lot of room for improvement and also miniaturization. So the question is whether this is an alternative to generating terahertz radiation compared to an electronic approach. And here in this picture, for example, you see just a picture of a terahertz standing wave, actually. In this case, atoms fluorescence. It's a standing wave which creates a potential and atoms then fluoresce. So just to visualize actually a terahertz wave. It has been demonstrated already over longer distances. For example, here at 650 meters. This was done by Professor Ducournau in France as part of the TOR project, created a 300 gigahertz bidirectional link. So changing to the next topic, which is also relevant to the demo today. One parameter which is very crucial is generally for wireless communication is the phase noise. Or generally for test and measurement, for many applications, phase noise is a very important topic. And we will see that actually later on in the demo as well. So what is phase noise? Phase noise reflects actually how good an oscillator is, which means how good the frequency, how stable it is. So basically, if you consider, as shown here, for example, a voltage or some amplitude, of course that finds the time. So you have a sinusoidal wave, an oscillator. It has a component with a certain frequency, but also a phase component, and this phase can change. So ideally, you have exactly one sharp peak, as shown here in blue on this picture. But in reality, you have some kind of drift, a short-term drift, which means seconds or less, and which leads to sidebands and effectively broadens your spectrum around this frequency. So you have the time domain in the upper picture and the frequency domain in the lower one. So what does this lead to in wireless communication? So in digital communication, you transmit information via different modulation schemes, QAM, for example. Here on the right side, what is shown is 16 QAM, for example. And here you see the impact of phase noise. So in this case, you have a kind of in the phi direction of the constellation diagram, you have a kind of jitter. So and that is due to phase noise actually. And if this becomes really bad, then this leads to bit error rates, and eventually you will not be able to transmit information anymore. So it's a very crucial aspect, and generally the higher you get in frequency, the more crucial this aspect becomes, and also maybe more difficult to control. So just to explain what we later see on in the demo, usually what you show on the evaluation or as phase noise is a single sideband phase noise. In the picture before, what you saw a symmetrical spectrum. So on both sides, but usually they are symmetrical. So for this reason, actually in display later on, one only shows a single sideband phase noise, which is only positive. It's just by convention. So the question is like, how can you measure this? One problem you always have in a measurement instrument is that you have instrument oscillator noise. Yeah, so in the instrument itself, of course, you also have oscillators. These themselves have phase noise. This means that the question is like, how can you measure phase noise below the oscillator noise of your instrument? And this is actually what the cross-correlation method was devised for. If you look at this picture, for example, you have a certain input, and this device under test, for example, has a certain phase noise and oscillator, and then the path is split up in two different paths. So into the instrument, in the instrument actually, and then you have two references, two separate oscillators in the instrument, which are independent and not correlated for this reason. You mix this with the different references, which means the output is then the reference with the DUT phase noise. And if you correlate then these outputs actually, then the part which is from the references from the instrument, which are independent, are not correlated. And what is left is only the correlated part, which stems only from the device under test. So this is a very, it's a way how you can in the instrument remove the instrument generated phase noise, and only what is left is the phase noise by the device under test. So let's have a quick look at how to generate microwaves, very stable microwaves. I very shortly go over this slide because later on Thomas will actually have a more in-depth discussion. So what one does is one has an optical laser. A laser always has a cavity, and when inside the cavity you have certain round trip time, which is defined by the length of the cavity. So what one starts is with the femtosecond pulses. The femtosecond pulses are generated with these lasers, and then this is converted. So in the frequency spectrum, you generate a frequency comp with a certain frequency spacing, which is defined by the cavity length. So the repetition rate is defined by that. So I think the beauty of this approach is the different parts, or the different frequency components in this frequency comps they have a fixed phase relationship. And this is kind of what is visualized here with this kind of gear. On one hand, on the left side, you have the different optical frequencies, the frequency comp, which are linked with this gear from the cavity. They have a certain phase relationship, and you can convert this phase relationship to a microwave, which you create by, for example, taking two of these frequencies. The application could be, for example, calibration. You can use this frequency comp for calibration, phase calibration, for example, of instruments, because, well, if you have a calibrated photodiode, for example, then you can trace this back to the phase of the optical frequency comp. So let's switch gears to another topic, which is also related to photonics, so-called orbital angular momentum. Actually, to me, this was a kind of unclear topic in the sense, because when I think about light or photons, I think about photons in terms of spin, right? So they don't have structure, but they only have they have a spin in one or both directions. Basically define the polarization. But actually, as it turns out, and this is actually a research field only 25 years ago it was discovered, even single photons can have an angular momentum, which is a little bit, it's difficult to imagine. So the question is, or how you can visualize this, is that, for example, you have a kind of vortex structure as shown here in the upper graph. This is the phase of the photon, and in the intensity distribution, then it looks like a donut. In the middle, because the phase, well, actually all phases, but there's no intensity. And then you have, for example, for a laser, you have always a cavity, and the kind of wave equation in cylindrical coordinates leads to these Laguerre-Gauss modes, and these have certain intensity distributions, which are shown here. And they are associated with certain angular momentum. Yeah, so basically, if you look at the lower part, you see kind of different structures. So basically, there are two different parameters which are kind of parameterizing these Gauss modes. And there's one in radial direction, you can say, which is P. So the higher these index P, the higher the number of rings, basically, right? So in addition, different colors, here you have the different phases of that system. So the question now is, well, you have single photons, but how can you visualize this, or how can you see this angular momentum? And it's quite interesting. If you, for example, change a number, or basically have a camera using optical high frequency photons, then you can could detect one single photon, and then over time more and more photons, and then in the end, the whole ensemble of photons gives you kind of the picture, the distribution, because always it represents a probability distribution to detect a photon at a certain place. But here, this is part shown, for example, in this upper picture, where you see the dots stemming from single photons, and then you get the distribution actually. And this is quite surprising to see this, that is possible to see even with single photons. Then just to mention here, superposition states of these modes are also possible. Yeah, so there are these modes are orthogonal, which means you can create superposition states of these as well. This is shown in the lower picture. So that is a technology which is interesting also for communication in the radio frequency. And there, for example, it has been already demonstrated also in experiments. Here you use an antenna array actually to create a phase shift, at the right position to create these vortex states. And this has been demonstrated, and even information could be sent over these. For example, this has been demonstrated in the D band by NEC at 150 gigahertz. For example, transmitting 256 QAM over 100 meter, and quite high data rate. And also NTT and demonstrated as well. Also other actually have now, this was some time years ago, have actually pushed the boundary up to 1 terabit per second, up to I think 1 kilometer. So it works. And the nice thing is it's an additional degree of freedom, kind of multiplexing technology. Of course, it's probably rather sensitive, yeah. So it can be used in certain environments, but definitely it's a very, very fascinating technology that it works actually. So let's quickly talk about channel models. So that's generally a question when we talk about terahertz communication. Always, the first step, also when standardization starts, will be to describe actually the propagation characteristics of terahertz communication in the channel, and in order to develop channel models, and this is then used for link level simulations and so on. So what one does in channel sounding is that it has a very short pulse. So this is time domain channel sounding, very short pulse at t equals 0. And then you send this into the channel. You get reflections from the environment, like a submarine, for example, has a sonar. And then you get basically a picture from the environment and the propagation characteristics as well. So we did this in the RNS campus, for example, for 300 gigahertz in the D band as well. Here's some overview shown on the left side. So this was an outdoor scenario where we have Tx fixed in a certain position and then Rx is moved. You see the green stars. So this was an outdoor kind of street canyon scenario. And we have an indoor environment as well, which was done in atrium. It is similar to an indoor airport or a shopping mall scenario, for example. And I think that how the setup is quite simple. We use our vector signal generators, the front end for the D band, on the analyzer side as well with the spectrum analyzer. And basically we send a correlation sequence, so functor.true sequence, and then later on do the post-processing, and basically it works similar like GPS. In GPS also you measure time delays and use also correlation sequences. That's the same what we do here. These are some example measurements. I mentioned this is a street canyon scenario, for example. The transmitter TX is fixed and RX is moved on this kind of card. And we compare this, for example, for the D band and the H band at 300 gigahertz. And it's published already. Yeah, here on the left side, you can see the channel impulse response from a distance, so short distance, 10 meters up to 170 meters. Yeah, and you see still, I think, this was done at 158 gigahertz, but you see that the signal is still visible and it's not the end of the sensitivity. Anyway, so we are continuing these activities now outdoor at different frequencies, but also indoor in a factory environment. So this is a campaign we did in January of this year, where we focus on the D band, so 160 gigahertz mainly, but also to compare it at certain points also with 3.7 gigahertz, which is the industry frequency in Germany, and also 28 gigahertz. And well, I mean, here you see, for example, on the lower part, this is the transmitter position, one of the transmitter positions, where you have actually this D-band front end on this positioner. And then in the lower part of the floor, we had the RX and moved it to different positions just to see the reception line of sight, attenuation, and so on. And on the right side, you see, for example, this one channel impulse response. You see the first strong line of sight and many reflections. Yeah, we extended this as well. So this is another example. Again, the same factory floor. TX is fixed on this kind of balcony, as you saw in the last picture. And then RX was moved from a certain position, closer distance to far distance. Yeah, and that's again so along a corridor on this factory floor. On the right side, you see the channel pulse response. So again, the channel pulse versus the delay. Yeah, in basically this is microseconds, and the green arrow shows you the direction, the movement direction of the on the factory floor. Yeah, so we go, of course, to longer distances, to farther distances, and because of that, the line of sight peak, of course, moves to longer times. And but you have a certain clusters which you can see actually all over the whole path. And this is, for example, could be from reflections from the wall and so on. So this is now being investigated. So now we come to the end of the first part on the theory background of how photonics can be applied in terrace communications. And now we would like to hand over to a real-life demo on phase noise measurement of an ultra-stable microwave system based on optical frequency comp. And for this, I will hand over to our expert from Optical Photonics, Thomas. So.
Thank you, Taro. I would like to continue the introduction of the frequency comp, briefly introducing the parameters, and then give the context to the later demonstration. So Taro already showed this slide. The basis of a frequency comp is a mode-locked laser. In our case, it's an erbium fiber laser oscillator. It emits sub-100 femtosecond pulses at about 200 megahertz repetition rate, and in the frequency domain that corresponds to a frequency spectrum of equidistant lines, which are separated by the 200 megahertz with a common offset towards zero, which is denoted as FCEO. The FCEO comes from the carrier envelope offset because in the time domain it corresponds to a phase slip between the carrier phase and the phase of the center of the pulse. In conclusion, every spectral line is given by an integer multiple of the repetition rate plus the common offset FCEO. This can be illustrated by the elastic tape model, where the lines are represented as marks on an elastic tape, and the two degrees of freedom of the elastic tape is that it's pulled or that it's overall translated. The two RF frequency, FCO and FREP, can be stabilized. In the case of FCO, an alternative approach is difference frequency generation. Because every line of the comp has a contribution of this common offset, the difference of two lines does not show any FCO offset. Therefore, it's a real multiple of the repetition rate. To do so, we use the spectrum of the oscillator, broaden it to more than an octave, and use the blue side minus the red side to generate difference frequencies, which are again in the optical at about 1560, to be able to use the Abrium technology for further amplification and different types of wavelength outputs. So at that point, the formula is simplified to be just nu n equals n times f rep. So that would be a rubber band which is pinned at zero frequency. So for the demonstration, we have the frequency comp, and in addition, we want to convert this pulse train into an RF signal. And because we want to generate high frequencies, we want to have more power in high frequency contributions. Therefore, we add an interleaver box, and inside the interleaver box there are 4 stages of fiber interferometers. Each stage will generate extra pulses in between the input pulses. So in the first stage, there's 1 extra pulse in between the pulse train, and in the second, the number of pulses will again double, and therefore in 4 stages we'll generate 2 to the 4, so 16 pulses per input pulse. If we then send this pulse train onto a photodiode, we'll get a spectrum that is shown here, and we still see all the harmonics of the initial repetition rate 200 megahertz, but most of the RF power is concentrated on the 16th harmonics at 3.2 gigahertz and the harmonics of 3.2 gigahertz. And for the demonstration, we want to look at the phase noise at 9.6 gigahertz with an FSWP from Broder & Schwarz, a phase noise analyzer, in 2 different scenarios of locking the repetition rate. In the first scenario, we pick up the pulse train from the oscillator and lock the 4th harmonic at 800 megahertz to an 800 megahertz RF reference. In this case, the phase noise that we expect at 9.6 gigahertz will be limited by the scaled phase noise of the RF oscillator at 800 megahertz. And in the second case, we use a low noise optical oscillator at 1550 to lock the frequency comp in the optical at 193 terahertz, and therefore the phase noise at 9.6 gigahertz will be the down-converted phase noise of this optical reference. Okay, for the demonstration, we now have a frequency comp which is offset-free and has up to 8 outputs. In this case, we are just using 1 high-power output, which is transferred into the lower box with the interleaver. And then on the back side, there's a photodiode, and eventually the RF signal is transferred via this cable to the FSWP. And we have an additional optical cable which goes back to the optical reference for the second part where we lock to the narrow line with optical laser. On the FSWP, you can see the spectrum of the photodiode, and as you can see, the first higher peak is at 3.2 gigahertz, which is 16 times the 200 megahertz repetition rate due to the interleaver, 4-stage interleaver. Then we can have a look at the next peaks, and there is also the peak at 9.6 gigahertz. Then we can zoom into the 9.6 gigahertz peak with a span of 10 megahertz and a bandwidth of 1 kilohertz, for example. Then we have to change the amplitude range to be 150 dB. And then we can see the narrow peak at 9.6 gigahertz with the side noise. And for the measurement of the noise, we switch to the noise measurement. which will now represent the phase noise from the carrier at the distance given from 10 Hertz to 1 megahertz. So if I run this, we see the phase noise measuring building up. And in this case, the frequency comp is locked to the 800 megahertz RF reference. So we can take this as reference traces. So we copy trace 1 and trace 2. So the upper one is the phase noise and the flat one is the amplitude noise. And now we can switch to an optically locked comp. And again, run the phase noise measurement. And what we see is that we see significantly reduced phase noise close to carrier, because now we are down converting the phase noise of the optical source to the 9.6 gigahertz. The reduced phase noise in the case of the optically locked comp shows the potential for the generation of low phase noise RF sources from optical frequency division. In this case, we are using a cost-effective fiber laser, but that can be significantly improved by using a Hertz laser stabilized to a high finesse cavity.
Okay, thank you very much, Thomas, for this fascinating demo, which combines the world of photonics with the world of electronics. And we're almost at the end of the webinar. So now I would like to just address one topic, which is kind of in this context, a little bit off track. So just a couple of years ago, in 2019, actually the kilogram, according to the SA metric system, has been redefined by photonics. And this is something I would quickly like to explain and conclude with. So as you see on the left side of this slide, this is the original kilogram in Paris, which is a bulk iridium platinum metal, basically. Which and the problem with this is, if you look at the drift of the mass over 100 years, that actually the drift is quite large. Yeah. So here in the middle, you see various copies of the original kilogram, and the drift in the mass in microgram, which is not so small. Yeah. And that's something, since the kilogram is of course part of the SI system, and it should be constant. That's not a state you want to be. So actually in 2019, the measurement of the Planck's constant has been improved so much that it's better or slightly better than the definition or the drift of the kilogram. And because of that, the kilogram has been redefined by the Planck's constant. So this means in the end that the new definition of the kilogram is that it corresponds to the energy of on the order of 10 to 40 photons at the frequency of this hyperfine transition of cesium-133. 10 to 50 photons, it's really a lot. I mean, it's completely impractical. So this is kind of the output power of a, I think, 3 megawatt power plant for 1 year, yeah, which is of course completely impractical. So what you now need to do, and this is actually something which has been done, one needs to find a connection, or the connection is there, but one needs to basically trace back this macroscopic kilogram back actually to the energy of the photon. And it's done in several steps. Actually, you start from the photon based and then connected to the electron mass again to the atom, then you have the silicon atom. And then actually if you're at the silicon atom, then what has been done, and this is shown in this picture on the upper left. So this is a monocrystalline silicon sphere, which has actually approximately 1 kilogram. And it has been completely polished. I mean, it's polished to the precision of that the valleys and the peaks on the sphere are on the order of 40 nanometer maximum. Yeah, so it's the roundest object on Earth. And so what one has to do now is basically to count silicon atoms. So one knows the lattice constant. One knows, so in a certain volume, how much atoms there are. And then now you have to measure this whole object. And this is what has been done. So this is the lower picture. You see this kind of silicon sphere in this vacuum chamber. So here one measures by interferometry actually the deviation from the perfect sphere. And this is what's shown in this kind of heat diagram. Yeah, you see, and this just reflects actually the crystalline structure of this particular sphere. And so anyway, this is a way how to connect actually the energy of the photon to the macroscopic kilogram, and I think it's a very nice example, and which means that now everything in our in the units and what we use in this I metric system are defined by natural constants, don't change anymore, and the better the measurement techniques become, so each of these steps actually will become better with time, then which means we have a better definition of the kilogram. Okay, so this is now the end of the webinar. Thank you very much for watching, and I hope we have other opportunities to update you on 6G topics in the future. Thank you very much for your attention.